Hello, my name is Nurulain. So today we'll cover the introduction of reaction engineering 1. So basically, production and importance of nitric oxide is a vital compound used in medicine. Industrially, NO is produced by the oxidation of ammonia at high temperatures using a catalyst. Byproducts such as nitrogen dioxide and unreacted NH3 must be minimized to achieve high purity NO for medical applications. Next, the study objective for this assignment is that we have to identify the best reactor system for maximum NO production, ensure high efficiency, safety, and economic feasibility. And lastly, the findings will guide us to the full-scale plant design. So basically, few consideration of reactor system is that reaction kinetics, catalyst selection, operating conditions, and also reactor configuration.
Medical-grade nitric oxide is crucial for healthcare, requiring a purity of 99.9%. However, industrial production introduces impurities such as nitrogen dioxide, ammonia, water, which must be removed for safe medical use. This study aims to develop an absorption purification system by selecting the best adsorbent materials, optimizing the reacting conditions, and also investigating the desorption and regeneration for sustainability. To design, there are a few key factors that must be considered. First is the adsorbent selections, including the isotherms, surface area, and pore size. Next is the column design, which includes the mass transfer zone, the height, and diameter. And the last one is sustainability, by reducing the cost of overall production. Our goal is to design an effective, cost-efficient purification system for the NO to achieve the highest purity in our product.
Now, let's talk about the kinetic ammonia reaction. The main reaction, ammonia oxidation to nitric oxide, occurs at 800 to 950 degrees Celsius and up to 12 atm, a study by Ruan in 2022. It follows pseudo first order kinetics with respect to NH3 in excess O2 and uses a PTRH catalyst for high NO selectivity while minimizing side reaction. A packed bed reactor with plug flow characteristic is used. The side reaction forms NO2 when NO reacts with O2 in the reactor. To minimize NO2 production, a high activation energy and low awareness constant were assumed. There are also some other assumptions that can be met. For example, steady-state continuous operation and also adiabatic system. Here is the proposed catalytic system to optimum NO production. The process flow diagram illustrates NO production via ammonia oxidation in a packed bed reactor under catalytic conditions. The chosen catalyst is the PTRH alloys 5 to 10% rhodium in woven gauzes. Since ammonia oxidation is a highly exothermic, a high platinum content lowers the reaction starting temperature, reducing startup time. Rhodium levels are kept low to prevent plant damage from rhodium oxide formation. Platinum ensures high NO selectivity, while rhodium strengthens the alloy, preventing catalyst degradation. PTRH alloys also have better NO selectivity than pure platinum, making them the ideal choice. Our Aspen HYSYS analysis shows that the best conditions for ammonia oxidation are 800 degrees Celsius and 8.2 atm. At 800 degrees Celsius, ammonia conversion is highest and NO production is maximized. Lower temperatures slow the reaction, while higher temperatures cause NO to oxidize into NO2. Pressure increases NO yield until it peaks at 8.2 atm with no further benefits beyond this point. This condition ensures maximum efficiency and NO production. Our production plant is designed for high efficiency and consistent output. Based on our process flow data, the maximum NO production capacity is at 56,623 tons per year. While this exceeds the typical 500 to 5,000 ton range, research on high pressure plug flow reactors confirm that capacity above 50,000 tons per year are achievable.
Hi, my name is Lee and I'll be presenting the next part. For ammonia oxidation, we need a reactor that can handle extreme conditions and a gas-phase catalytic reaction. Among the options, the plug flow reactor is the best choice as it provides a controlled reaction environment with high efficiency. However, to further optimize performance, we proposed a packed bed reactor which builds upon PFR's characteristics. The PBR allows for catalyst packing, providing large surface area for reaction, improving efficiency and selectivity. This ensures that reactants flow through the catalyst bed in a controlled manner, maintaining uniform contact and minimizing unwanted side reactions. Additionally, the PBR effectively handles high temperature and high pressure conditions while reducing pressure drop compared to fluidized systems. These features make it highly suitable for ammonia oxidation where catalyst performance is critical. Next, for sizing, we achieved conversion rate of 94.55%. Using a Levenspiel plot and comparing calculated reactor volumes, the PFR/PBR requires only 0.274 meters cubed, which is much lesser than CSTR, making it the most efficient choice. For dimensions, a length of 35 meters was determined using Espen-Heis's sensitivity analysis. This ensures maximum ammonia consumption before the reaction plateaus while maintaining proper residence time to avoid side reactions. Moving on to catalyst weight, calculations show that at least 240.7 kilograms of plutonium-rhodium catalyst is needed to sustain the reaction at optimal rates. Additionally, we accounted for the expansion factor, as the gas phase reaction increases total moles by 9.625% as calculated. This was a key factor in optimizing reactor conditions for efficiency.
To calculate the concentration of inherent impurities, we are using the ideal gas law C equals to Yp/RT, whereby in this reaction, we are setting up the pressure as 8.2 atm and the temperature as 1073.15 Kelvin. This calculation helps us to identify each impurities in the NO gas stream. This data is crucial for designing an effective adsorption system to remove NH3, NO2, and H2O, which ensures a high purity of NO for industrial applications. In the industrial production of nitrogen oxide from the oxidation of ammonia, impurities such as nitrogen dioxide, unreacted ammonia, and also moisture can compromise the quality of the product. To ensure high purity NO, we implement a multi-layer adsorption system designed to sequentially remove these contaminants. The first layer utilizes the impregnated activated carbon, which is an effective adsorbent for the removal of nitrogen dioxide. This material is chemically treated to enhance the oxidation capacity, converting the NO2 into a stable surface species or reducing it into nitrogen gas. The second layer consists of zeolites, which is selectively adsorb the unreacted ammonia. Their ion exchange capabilities and micropore structure allow them to trap efficiently the ammonia. This step is crucial as even trace amount of ammonia can affect the downstream application. The final purification layer consists of metal oxides such as manganese oxide, copper oxide, or alumina, which is providing the additional NO2 removal. This oxide catalytically react with the NO2, further reducing its concentration in the gas stream. These enhance the stability of the adsorption process and ensure the consistent purification.
The chosen isotherm is Langmuir isotherm because it describes adsorption on a surface with a fixed number of active sites, where each site can only hold one molecule. This means that adsorption forms a monolayer, and once the surface is fully occupied, no further adsorption can occur. Additionally, the Langmuir model assumes a constant binding energy between the adsorption surface and the adsorbate, meaning that all adsorption sites are equally active. The process is also reversible and eventually reaches equilibrium. This model is commonly used in the adsorption studies because it provides a clear and quantifiable understanding of how molecules interact with the adsorption surface. In conclusion, our multi-layer adsorption system consists of impregnated activated carbon, zeolite, and metal oxide, each targeting specific pollutants. Activated carbon removes nitrogen oxide through oxidation, zeolite captures unreacted ammonia, and metal oxide enhances nitrogen oxide removal, ensuring efficient purification. We chose the Langmuir isotherm because it assumes monolayer adsorption and homogeneous adsorption sites, making it ideal for our structured system. It provides precise predictability and enhanced adsorption modeling, allowing accurate estimation of adsorption capacity and system efficiency. The fixed bed adsorption column is designed with a multi-layer downflow configuration, a 1.3 meter bed height, and an 80% mass transfer zone for optimal adsorption. The gas flow rate 100 ml per minute and superficial velocity of 0.3 meters per second ensure efficient gas purification. In summary, integrating Langmuir system with a multi-layer adsorption system enhances pollutant removal, making our design highly efficient and practical for gas purification.
Now, let's move to the design of an adsorption column for NO purification, focusing on the removal of NO2, NH3, and residue gases to achieve high purity NO collection. Our design used a fixed bed adsorption column chosen for its high yield, simple operation, and extended gas adsorbent contact time. Unlike moving bed system, it allowed longer interaction, ensuring efficient impurity removal. This column is also made of stainless steel, offering high corrosion resistance and mechanical strength, essential for handling reactive gases like NO and NO2. To enhance efficiency, we also implement a multi-layer adsorption system where different adsorbent target specific impurities, and also a downflow configuration ensure better gas-solid contact and reduce pressure variation. Let's discuss the key parameter. First, the bed height is set at 1.3 meter within the range 0.3 to 1.5 to balance efficiency and cost. Second, the mass transfer zone is optimized for 80% bed utilization, preventing material waste while ensuring high adsorption.
Third, the column diameter is determined using a superficial velocity of 0.3 meter per second and a gas flow rate of 100 milliliter per minute to maintain effective adsorption without excessive pressure loss. And here our key calculation validate this design. The HMTZ is 0.26 and the column diameter is 0.00266 meter, ensuring optimum flow. And our bed height to MTZ ratio falls within the recommended 5 to 10 times range. This confirms both feasibility and cost effectiveness. So how can we achieve its efficiency to 99%? We refine key parameters mentioned before, which are multi-layer adsorption system, optimized operating condition, MTZ, and downfall configuration. Other than that, regeneration strategies should be implemented to prevent adsorbent saturation. We use chemical purging with HNO3 for NO and NH3 removal. Also, thermal swing absorption TSA for desorption, where activated carbon is regenerated at 220 to 370 degrees Celsius, while zeolite requires 200 to 350 degrees Celsius to extend adsorbent lifespan and reduce waste. To ensure long-term efficiency, we implement real-time monitoring, scheduled maintenance, and structural inspection to prevent failures.
To conclude, the proposed PBR with PFR characteristics ensures optimal ammonia oxidation under extreme reacting conditions. Achieving 94.55% conversion rate, the reactor operates efficiently with minimal volume while maximizing catalyst utilization. With a production capacity of about 57,000 tons of nitric oxide annually, the design effectively balances performance, selectivity, and operational feasibility.
The reason we chose Langmuir isotherm for this project is that although our system involves multiple adsorbent layers such as zeolite, metal oxides, and activated carbon, each layer functions independently as a monolayer. This aligns well with the assumptions of the Langmuir model. Additionally, Langmuir isotherm offers precise predictability in adsorption studies. It allows us to accurately determine absorption capacity and model breakthrough curves, which are crucial for designing an efficient adsorption column in gas purification processes. Other than that, Langmuir isotherm also assumes homogeneous adsorption sites. In our project, zeolites and metal oxides exhibit uniform surface properties, which means adsorption occurs consistently without significant molecular interactions affecting the process. Lastly, the Langmuir isotherm provides enhanced adsorption modeling by defining capacity limits, making it ideal for optimizing adsorption efficiency in our purification system. This ensures that we can maximize adsorption performance while maintaining a well-defined structured approach to the process.